All right. Hey there, folks. Afternoon. Afternoon. How we doing? Good, good, good. All right. So just a quick update here. All right. 2603 March. Oh my goodness. Okay. So up on your should be an announcement. That announcement up, or do you need another minute here? Yeah. So our intrepid TAs are putting up an announcement for your projects. You have a project plan, and there's details of the project plan in the announcement that'll be due Thursday next week. So that's going to be March 12th. At 5 p.m. Okay? TAs appreciated meeting with all y'all. Now we think it's a good time to get some more detail out, and there's some details in the assignment y'all can follow. Okay? Get you started on those. So on Thursday, we did sort of a detour into some unsupervised learning methods, a little bit of clustering and things like that. We're going to get back onto the train of neural nets, okay, today, because we've done so many examples that are pretty simple, meaning that we have regressions, and we've done a lot of line fitting. We're trying to give you a little variety from other than just fitting lines, which I love fitting lines. I wake up in the morning, sometimes I just want to fit a line. Okay, I'm sure we all have that feeling in the morning. Thank you. Yes, I'm glad everyone agrees, perfectly genuinely. All right, but a lot of what made machine learning just such a so bananas, gangbusters, and interesting is that once we realized we could do a lot with images in machine learning. Okay, there's a classic cartoon that I should have pulled up for today. It's one of those geek cartoons. I don't know if it's XKCD or something else, where the joke is like, it's like, oh, hey computer scientist, can you take this picture and then upload it to the cloud and do all these operations to it? It's like, sure, yeah, no problem. This is a cartoon done like in the early 2010s. Okay, and then they said, okay, can you make it out? Can you write a program that tells you if there's a bird in the picture? Like, well, that'll take 10 years of research. Okay, but guess what? We can now have very good algorithms to tell there's a bird in a picture. Extremely good. Since the time of that little cartoon, it's actually gotten quite good. Now, we have covered to date, so for neural nets, so the topic for today is what we're going to call convolutional neural networks. We're going to cover it in sort of broad scale, but we're not going to be implementing it by hand today for sure. I'm not sure we'll ever quite be implementing it full by hand, but or CNNs, convolutional neural networks, or CNNs. Okay? All right. So, CNNs. Let's motivate to say, okay, let's consider performing a classification problem on an image. Okay? Now, an image, we're talking a photo, okay, especially in the digital world. We're not dealing with old-timey analog photos, digital photos. We have a bunch of data in pixels. Looking good on the stream, right? Fantastic. So the image, you got pixels there, right? Tons of pixels, tons of pixels. Okay? Now let's say we wanted to put this through some classification network, and out comes bird slash not bird. Okay? Now, in theory, this classification network could be an artificial neural network. You can throw as many layers as you want, deep layers, wide layers. And in theory, if they were big enough, and you give it enough training data of examples of birds and not birds, it can tell the difference between the two of them. Okay? But there are some technical challenges to this because the sheer amount of input data, all those pixels. Anyone heard of a megapixel, or do people not talk about megapixels? That's still a thing? Back when in my formative years, digital cameras were becoming a thing you could buy. Like, ooh, 1 megapixel camera? Oh, no, I got a 2 megapixel camera. Wow, right? Now they, does anyone know like how many megapixels are on their phone camera? Anybody even know? I don't know. Good enough, right? It's only if you're doing, like, ironically, bird photography. Feel like you need lots of pixels. Okay, this is going off the rails here. But if you're doing birding, taking photos, pixels are zoom, right? The more pixels that you have, there's a little tiny rare bird. You don't want that to be a potato, in pixels, right? So, unless you have doing bird photography, you have lots of pixels, right? Probably 10, 12 megapixel camera, okay? Right? So this is the input. Okay? And the output's some classification, bird, not bird. And you can imagine that that's some kind of CAN-H or something, right? It's like probability that it's a bird. Is it a bird, not bird? On, off to come out of that network, for instance, right? But the big difference is the number of pixels that go in. A megapixel is roughly a million pixels. A lot. Million, mathematicians will tell you, is more than 1. A lot more. What are the implications for that, right? On our neural net, okay? So if we have a neural net, so you say you have an input, okay, with lots and lots of inputs, okay, then you have to send them into some number of layers, right? Typically, you want a lot of neurons. So these are your neurons, the different activation functions. We'll give like a CAN-H activation, let's just say, just for example, right? Now, look at how many weights that you have to deal with, right? You have a lot going into a lot. Okay? So if our neural network were fully connected or dense, you might recall when we were doing our coding in Keras, we said, oh, we want a dense layer, right? That means that everything is connected to, the input is connected to everything on the next layer. Every single one, every combination, right? We're fully connected, dense, that is, yeah, we're going to redo dense. Like my handwriting, dense, all right? We're fully connected. Then there would be an impractical number of weights to tune or optimize, right? To train. Tune, train, optimize, you're changing the weights, right? That's bad, okay? So what you would do is literally you list this, like this is pixel 1, this is pixel 2, all the way up to pixel 1,000,000. Into the 6th, it's a lot, 6. To the 6th. So can't quite, not really very practical to use a fully connected neural net. And people have known this for a very long time, decades. Not a good idea. Okay, so how do we get around it? Well, certainly, one thing that would be nice is if we were able to get rid of some of those connections. Maybe we don't have every connection. I see some knowing nods, right? You already know the answer. Let's go. Okay. Do you want to lecture? It's cool. I need a break, honestly. Subscribers a lot to deal with. I need a break. Let's go on here. So, all right. No, we're good. Just teasing. I like the engagement. This is awesome. So you can get rid of some of them. But how? What's a good idea? All right. So now, Nick, ready? Okay. We're going to try something. But don't get too excited, okay? We're going to try something. We're going to live. What could go wrong in a live demonstration here? We're going to try to take a photo we just took, all right? Let's see. Back to here. All right, okay. Nick, my intrepid TA. Nick, say hello to the camera and the world. Hello. Yes, thank you. All right. So Nick's going to take a photo of me, okay? Actually, unless someone wants to volunteer to be on YouTube, okay? They can join me in the photo. No pressure, but you have exactly 10 seconds to comply if you do. All right, okay, or 20 seconds. All right, slowly come up to the screen very safely. If you want to be in the photo, okay, we're all going to stand side by side in the photo, okay? Okay, all right. You can keep in mind, you will be on YouTube if you do this. I know that's everyone's fear. Okay, all right. All right, okay, okay. All right, this is starting to get, okay. All right, what's up? That's okay. I'm sure the algorithm will work fine. Okay. All right, just come on in. All right, folks. All right. Okay. Everyone say machine learning. Machine learning. All right, got it. Okay, fantastic. All right, Nick's going to send that to me as a JPEG. Okay. All right. All right. As he's going to work on that. So. Okay. Audio is good. Yeah, it's starting to drop now. Yeah. It's about 30. That's not fun, but okay. I have a recording, so we can re-upload after the fact. Okay. All right. So Nick, you can give me that JPEG as soon as you can. Okay. And we're going to try. We're going to actually use a little bit of actually MATLAB today. You can do the same thing in Python. I can just do this really quickly in MATLAB. You can do the same thing. We're going to try this because what we need to do is find what's a smart way to not have to use every single one. Let's go back to here. Every single one of those weights. Okay. Well, what's often important in an image? Okay. Like if you want to know if there is a cat in an image or a dog or a bird, right? The thing you might want to look for is the outline, okay? Something that looks like an object, okay? So you're starting to see, by the way, there's a bit of an art to how we put together these neural nets. It's not just a magic, like it's not just any old neural net will get you what you need in a practical sense, right? We have to be a little smart about it, okay? So what if you could determine like what the edge looks like? What's the edge? Okay? In fact, when we are drawing, a cat, my best work. Okay. All right. What did I just draw? Well, yes, the outline. A cat. Yes, a cat. But I indicated what it was by the outline, right? Outline's important. Now the outline you can get by maybe comparing the color of one pixel. Let's go do a zoom in on the cat. Okay. All right. One pixel of the cat right there to the one right next to it. The value of those pixels are probably very different. Whereas if you're in the inside of the cat, well, you're probably a veterinarian. But if you're also just the inside the image of the cat, then you're probably, like, it's probably going to be a similar color, right? So maybe we should we should only include weights for neighboring pixels. Okay? Maybe we'll try that. Maybe so let's try to detect key features like edges bad on the maybe I can try restreaming. We'll keep going. Can you just hear it? Following. This is not me. This is Florida State University problem. This works fine for my house. Okay? All right. So, all right. Don't let that and keep you from enrolling. Okay. All right. Okay. The features like edges. So let's focus on the effect between neighboring pixels. Neighboring pixels. Let me know if we're good on the. Oh, you already? Oh, wow. My intrepid TA here. Okay. All right. You send it to me. Have it. So, file. Okay. We're going to download that image. Okay. See if this works. And I'm pulling open MATLAB. What was that? Testing. Pulling open MATLAB. Okay. All right, gonna drag this to the desktop like all organized people do. Okay. All right, and all right. This to work. Side so you can see. And see if this works. There we go. There we go. That is our photo, okay, of our participants, or willing participants who agreed to be on camera, right? Okay, good. So we have our participants here. That's an image, right? So awesome. And what I did is I just went into opened up MATLAB. Now you're all mechanical engineers. You have used MATLAB before, okay? So MATLAB is just a very simple scripting environment. The MATLAB, what does the MAT stand for in MATLAB, friends? Matrix, yes, exactly, right? Okay. What's that? Matthew. Lies. So, all right, let's and Nick, if you could reorient the camera to my height here, would be great. All right. So, all right. So what we're going to do, so what I did is I took that image and I just dragged it into this directory here. And MATLAB has all kinds of image processing cool stuff. And hopefully I remember to install it. Let's try it. So if we said, let's say that data equal to imread the image, so image to that JPEG. All right. Okay. Okay. I forgot there's a semicolon and I regret it immensely. Okay. But what am I looking at here? Those are, well, they're numbers. Good eye. There's RGB values from 0 to 255. Okay. 0 is black. Is off. 255 is on. So if it's the R channel, it'll be fully red. Okay. All right. So we have in data here. So if I were to say, let me just do a quick close all. Perfect. You're great like that. I'm just do, sorry, clear. Okay. CLC. I'm going to do an im show my data. Okay. Did I not save it as data? What? Did I not save it? Data. Why did I do that? Okay. Im read data. Im show data. It's show image. Okay. All right. Come on. Show me that image. There we go. That's in MATLAB, right? You can plot. Did you know you can plot images in MATLAB? Well, now you do. You can do so much cool stuff in MATLAB. Sorry, we're taking a detour into MATLAB. Python diehards, just have a nap. Okay. All right. It's pretty cool. All right. So look, that's an actual MATLAB plot right there, right? Okay. And you know, MATLAB is matrices, and that data is stored in a big matrix where you have. Let's actually look at the size of the data. Look at the size of the data. 4,000, 5,000 something. Oh, it's a three-dimensional matrix. What's a three-dimensional matrix called, friends? Tensor, right? It's a tensor. What's that? We're all right? We're okay? We're doing okay here? The tensor, right? What do you think the 3 stands for? Red, green, and blue. 3 images, right? So what I'm going to do, so right now, so that's a color image. And just for the sake of our argument, I'm going to turn this into a black and white image. So I'm going to do a few things here. So I'm going to just average all 3 layers. So it's sort of like a mishmash of black and white, okay? We'll go to monochrome here. So let's see, we'll call it a black and white image, BW image, okay? I'm just gonna do a sum of my data across the third dimension, which is my RGB, okay? And remember a semicolon, okay? Then check the size of my black and white image, okay? And look, oh look, it's a 4,000 by 5,000. And if I do 4,000 by 5,000, how many megapixels is my camera? So if I do answer 1 times answer 2, that's the number of pixels. That's by the way, clearly, that's like the number of rows and columns in my image, right? Right? What that is. So 1 times the other. So this is a 24 megapixel camera, roughly. I mean, megapixel is not exactly a million, but it's 24 million. So that's 24 million pixels that we captured this beautiful image in for all eternity. Okay, all right. So now we have all those images. So now this size this is an image, and now it's a bunch of stuff that's added together. Technically speaking, it should be an integer. The image pixels have integers from 0 to 1 to 2 to 3. I want to see if it stayed an integer after I created the new image. So I'm going to check the class, and it tells me it's double. Anyone know what double means? We know what double means? It just means it's a floating point number with double percent decimal point, right? So if we want to show what it looks like, we have to turn it on with an image. We have to turn it back into an integer. So we're going to say that black and white image. We're just going to turn it into an integer. We're going to say uint, which means an unsigned integer, meaning there's no negative signs. We don't want negative pixel values. That's for the advanced class. I have no idea. I'm making that up. So with 8 bits, this is just the word for it. So BW image. This should turn it into a unsigned 8-bit. Hey, you know what's 2 to the 8th power? 256. 8 bits. So now let's im show. Close everything. Im show. Put black and white image. Okay. There we go. Yeah, it's a little bright, but we can sort of see what's going on here. Okay. I need to divide it by 3. Divided by 3. I forgot, you know, that's the important part of an average, is dividing by a number. The more you know. Thank you, Jack. Divide by 3. Okay, let's close it all. All right. There we go. This is your fault, Jack. All right. So there we go. Look, that's our image, right? We can still see what's going on. Okay, sort of, kind of, right? So yeah, I'm going to multiply it by 2. You know what? No, that's right. Did it okay. So now we have the black and white image, right? So now let's see what happens. Let's just do a very simple operation where we're just going to compare a pixel to the pixel next to it. Yes, question. Yeah. I could do mean. You know what? We're going to go back and do mean because I think I screwed everything up. I just realized because I overwrote. I limited to 255, and then I added, so they're probably capped at 255. This is Jack's fault. Boo, boo. All right. So let's go back to the im show. Let's go back to BW image is equal to mean. Do that because then we can. I just realized and then we'll just turn it into a uint. Unsigned integer 8, and all on the same line. See what happens. Now we're going to close all. Now we're going to im show. There we go. That's a little better. Hey, yay! Thanks, Jack. Actually, thanks. What's your name again? Ulysses. Thank you, Ulysses. Yay! This is now a war between you two, right? Who can help it? All right. All right. All right. So here we go. We got it. So, all right. So we have black and white image. Now, what I want to do is I'm going to try to take each image, each pixel, and I'm going to subtract it from the pixel. I think it's either to the left or above it, but either way, it's going to be the pixel of the index right before it. So for instance, if we have BW image, I can index this into it by saying row column. Hey, what's my 10th row and 10th column, right? And it'll tell me, hey, dummy, it's 121. Well, I inserted the dummy. But right? Or you could always insert, you say, hey, I'm just gonna give it one index, and it's just gonna go down my columns first, and then the next column, then the next column, then the next column, right? So the first image is that, the millionth pixel, that. I'm gonna try to take each element and subtract it from the previous element. So it's going to be like some positive, negative thing. In fact, I should probably turn it back into a double to do that. So let's create a new, we'll call it M2. Let's make a double. That way we can get negative numbers out, because an unsigned integer. Does an unsigned integer have a sign? It does not. Very perceptive of you. Okay. All right. So double, be the black and white image. I'm just going to, yeah, black and white image. Okay. All right. So I'm then going to say, I'm going to call it an image difference, okay, is going to be equal to M2. I'm going to do this. I want to get everything. So from the second pixel to the end, minus M2 1 colon n minus 1. So from the second to the end, now I want to subtract the one before it, okay? This will give me one less pixel than I want, so I'm going to try to fit that in back somehow, okay? I know what try this again. So make sure that math works, okay? But we're missing a pixel because we're leaving out one of them. That's going to yell at me something. That's going to bite me in the tush. Okay. What I'm going to do is I'm going to create a M3, which is M2. Okay. It's equal to M2. Then I'm going to say, hey, M3, I want everything but your first pixel now be equal to, aha, so I preserve the right size. You believe me? You're making a expression. You believe me? That makes one of us. Great. So, all right. Okay. Now, this M3, this image 3 should be all the differences between one pixel and the next. One, the next, and the next, and the next. So, all right. Should be positive and negative numbers. What's going to happen? Can I do an ImShow on M3? Let's find out. Close all. ImShow on image 3. Ooh, look at that. I mean, look, there's a lot of noise and stuff going on, but you can sort of see yourselves, right? Now, you see the features right there? Little edge detection. Look, this is a completely uncontrolled experiment. We did it live, right? This is like the dumbest edge detection imaginable. Extracting one number from another, right? You can see, because we did this nearby, like by comparing to nearby pixels, you can start to see, look at that smile. Look at that weirdo. So, right? So yeah. So there's something to comparing nearby pixels, right? But how do we do that in a systematic our convolutional neural networks, okay? All right, that cat. All right. So this motivates our choices in these convolutional neural networks to look at nearby pixels, okay? Right. So this motivates looking at nearby pixels. Okay. All right. Back. I'm going to go back to here. Looking at nearby pixels. And another thing I'll point out, back to here. Yes, you can see little bits of the faces, right? And yes, the rest is kind of like random. Another thing to think about is, like, if it's random noise and we sort of averaged any area, right? That should just be nothing. Random noise. I say noise. You know what I mean by about that. It's just random signal. If it's purely random, you average together, it's going to wash out and be nothing. But then you see little. You see things which are, you know, more black right there, right? Average those together. That's less random. Those nearby pixels. They'll be more dark on average. Imagine blurring this. So it motivates two things. Looking at nearby pixels, and then pooling together thank you. You don't want to be on MATLAB too long. Like staring into the sun. Okay? Thank you. Motivates looking at nearby pixels and then pulling together the results of network output, of neuron outputs. Okay? That's just like a really high level, hey, look at that. Isn't that neat? Also, look how easy that was in MATLAB once I remembered how to type things. Okay? All right. So that's essentially what convolutional neural networks do. They give you an operation that operates on nearby pixels. There's no need for a pixel all the way over there to directly interact with a pixel over there. Okay? You do some operations nearby, then you group them together. Okay? And eventually they will be grouped and pooled together. So that way, eventually there will be some comparison between over here and over here. But by then, so much of the complexity of the network has been simplified. Okay? So, all right. So convolutional neural network. Okay? Convolutional neural network, or CNN, employs at least one convolution in place of a matrix multiplication in at least one layer. Okay? All right? So recall that when a dense neural network has signals coming in, you multiply the weights by the weights by the inputs, and you add the biases, and they come together, right? Like and we turn that into a matrix multiplication when we were doing our feed-forward neural network, when we were in our forward pass, right? Okay. Now, here we have a convolution. Does anyone remember what the phrase convolution from any other class they've taken? Maybe as mechanical engineer. Taken it. Lie to me. Make me rhyme. Differential. Yeah, yes. Differential equations, yes. Okay, did anyone cover convolutions and differential equations? No? No? Is that a 6-7 thing you're doing right there? I don't know what that was. Okay. Sorry. I apologize to the world. So convolutions are a trick that you use when you're doing Laplace transform. Okay? So recall, so recall a convolution from Hubicki / Laplace transform. Did you all cover Laplace transforms? Good. Calculus in disguise, right? Trademark TM. Okay? The idea is if you had two Laplace transform terms, you want to multiply them together, you don't just multiply them together, you run what's called a convolution. Okay? So now, the idea is that you have some convolution, S of t is the integral of some function, x of a, there's some wt minus a dA. So it's the integral of two multiplied functions. That's the idea. Okay? Gesundheit. Well, I thought we were all working from a common understanding of what a convolution is. Turns out I need to change my entire game plan here. It's all right. Because this convolution and the convolutional neural network is just kind of like this. Okay? Yes. Okay? And typically, it's denoted as some asterisk, where S of t is equal to x asterisk w of t. That's the convolution, that little asterisk. Okay? Okay. But the idea is that the integral of two multiplied functions. That's the general idea of it. Okay? Now, we are not dealing with integrals of continuous functions when we're dealing with pixels, okay? Instead of integrals, we might be just adding things, okay? Adding across these different, that's like, integrals are kind of like adding, right? I'm being super rigorous in my math right now, as you can see. They're kind of like adding. So integrating across pixels is kind of like adding pixels together, right? So now, imagine, So in CNN terminology, convolutional neural network terminology, okay, we convolve. How's that for a word? Convolve. That's not written in my notes. I remember it's called convolve. It just came out of my brain, okay? Make it a thing. It's convolve. We convolve an input. Think of that as your image with what we call a kernel. Okay. The kernel is kind of like a base. It's sort of like a template that we decide that's an important structure that we're sort of map this onto it. Okay. This sometimes can be called a feature. So when you take your image and you sort of map it onto this kernel, it becomes what is often called a feature map. It is sometimes called a feature map. Okay. So in this case, let's say we have some S, that's going to be our feature map, that's the output, is equal to your image I, your input I, involved convolution with K as your kernel. Kernel? And we'll show you mathematically what that looks like. Your kernel, that's your input. Think of that as your image. Or it could be an image after you've convolved it already. You put a convolution into another convolution, okay? Right? This is your output. Okay? So instead of being an integral, you have that down. I'm going to go up to my integral again just to scare everyone. Okay? Don't show me the light. Holy water here. Okay, look at this. Right? So, right. The idea is that you have some function where you evaluate it of A, okay? Then you take some other function and you evaluate at some other point that's dependent upon A. Then you integrate over some range of A. Okay? So you're kind of moving across these two functions, okay, at different rates, and that gives you a multiplication. Then you add it all up continuously in an integral, okay? And that's useful if you're doing Laplace transforms, which helps you solve differential equations analytically, for those of you who like that kind of thing, all right? So, but here, it's very analogous, but not exactly the same. Where if you have some Sij, where this is a grid or matrix of data, you're indexing with some row, some column, kind of like in an image, right? Equal to the convolution of ik evaluated at ij, how we write it, okay? But mathematically, is the sum of the sum of your input image mn times k I minus m j minus n. So m n. So you are summing, insight, across your m and your n, okay, for each I. So you can run this operation for each row and column I and j across some range of m and n. Okay? So you can see, look, it's a multiplication of two functions, then you add them up or integrate them. So it's analogous to a convolution. Okay? Right? And you could also write this similarly. So it's a commutative property of convolutions, just like a times b is equal to a times b, as long as it's not a matrix, right? You can commute by switching the order. You can also say that si comma j equal to the sum across m, sum across n of I minus m, j minus n, k, m, n. And you can see how it creates a new output image by pulling an operation on nearby pixels, kind of like we did with a super simple edge detection. Okay, let's do the super simple subtraction, right? This is just a much more rigorous version of that. Okay? So that's your convolution. That's what a convolution layer would do, as opposed to just taking in all of your weights, multiplying by the outputs, and adding them together, i.e. a matrix multiplication. Okay? So moving on. So that's the convolution operator. Okay. Now, another important thing is that when you have an output of a network, yes, we found a way. So if you're looking at, so now, when before we had, so before, for a fully connected, okay, you will have all kinds of all those weird crosshatch patterns, okay? So now we are going to be more sparse, where we might have where there is no thing going all the way over there and over there, right? Apologies for my really gross cross-hatching pattern, but the point is you got to go all the way across, right? Okay. Before it's fully protected, now it's more sparse. That's nice. Fewer weights to tune. Okay. So there are fewer weights. Isn't that nice? You have fewer weights to tune, you probably need less data, less compute time to actually train your network, okay? But there are other ways that you can reduce the number of the number of parameters. You could say arbitrarily that, hey, all of these weights like this that go straight ahead, let's make those all the same. Let's make them share the same parameter. Let's tie those weights together. So you don't have an individual weight for every connection. Some of them are tied. So you can also share parameters by tying weights together. Sometimes you can call that a weight-tied network. Which kind of makes sense because you might be doing very similar operations just repeated many a time at different parts of the image, right? Okay. All right. Tie some of them together in the network. So you can make it sparse, you can tie some weights. So sparsifying and tying weights can make a network more tractable or easy to train. Okay? You don't want to tie too many of them together because then it's not doing anything, right? All right. Finally, today I want to talk a bit about another stage in a convolutional neural network called pooling. Okay? Listen tight. We alluded to this before, that even though we are sparsifying the network and we might be tying weights together, at some point we're going to probably want to like distill this down into like just a number or two. Like, is it a bird? Is it not a bird? Okay? Meaning we're going to probably want to start taking the data and condensing it instead of having what I have 20 million pixels. Condense it down to fewer and fewer. Okay? So an example here. So pooling reduces the size of an image. So I would say image, or when it's just generally say gridded data. Okay? Size of an image or gridded data to a lower resolution grid. Okay? For instance, let's just say we have this grid. This one's easy on my carpal tunnel. It's just 4 boxes. Okay? I don't have carpal tunnel. I'm lying. Okay? And there's some numbers, say 0.1, 0.5, 0.8, and 0.4. I could do something I call a max pool, which takes those 4 numbers and turns it into the maximum of those. Value is 0.8. I've pooled that data together to a maximum. So if these numbers, for instance, were the result of some activation of networks and weights, right? Perhaps it represents like, oh my goodness, this is the most bird-like thing in this image. Ooh, that means this whole area, this is somewhat bird-like. This is me anthropomorphizing a neural network, right? But as a result, this becomes a smaller layer of the network. You could pool and pool and pool and pool together, then by the end, you're like, here's a number. Is it a bird? Right? So now, other layers of the network, happily to make those all kinds of activation functions. They could be your tan-H's, they could be your ReLUs, be a swish, or sigmoid. Okay? But for a convolutional neural network, you need a convolution, right? And you will almost certainly be using pooling. Okay? And that's what makes image classification feasible with a convolutional neural network. And it's not just convolutional neural networks, okay? It's not just images, okay? So it's not just images, okay? But any gridded data or data where proximity of samples matters. So, I know some people work in wind tunnel stuff right here, right? Wind tunnel research. And so, yeah, you can take a Schlerin image of your Mach 5 wind tunnel thing. I don't know what I'm talking about, right? And you can use a CNN to help put that information together, pull it down, try to use it to demonstrate what you want to demonstrate, right? Or it could just be gridded data that you grid together. For instance, time series data. Okay. Let's say you're just looking at you're feeling the pressure against the wing of an aircraft. Okay, let's say you have all these pressure sensors on the wing of an aircraft, and you want to be able to classify if I'm feeling this pressure right now, and over the last several data seconds, this is the pressure I was experiencing. I want to predict the pressure I'm going to experience next, right? It's not those points in time aren't arbitrary. The fact that one happened after the other is important. There's dynamics to it, right? Kind of like predicting the trajectory of this pencil, which I hope I don't drop. Okay, right? The fact, if my individual data point, if there was no relation from the fact that the pencil was there, then there, versus there, then there, then there, then there, all over the place, the fact that then this would be nonsense garbage, okay? But the fact that it's going through a trajectory, I can measure that over time. It's like, oh, here's the position over time. Now try to predict where it's going next, right? At which point, you might have a grid that looks like this, where you have time 1, time 2, up through some time n, and here's all these different data values on this axis. These can be other measurements, right? Measurements. Guess what? You have gridded data. You can use a convolutional neural net on that. Okay? Why is that important? Well, because nearby information is important. And maybe it's not super important that it correlates what's happening there to all that time over there. So it's not just images. It's just really obvious when you're looking at an image at this. Okay? So when you're thinking about your projects, you're like, okay, am I trying to do anything with time series data or any kind of gridded data? You're doing like a temperature thing. You're looking at an oven, and it's like, okay, what is the temperature values across that oven? Maybe you have a couple of temperature sensors throughout. Well, maybe they're in a grid nearby to each other. So certainly these two sensors over here that are close to each other, they correlate more to than what's over there. So maybe you take that gridded data over time and you CNN it. Okay? All right? Questions about that? Yeah. Yeah, so you're mentioning, if you had a robot and you had states, I'm currently in this position, and in that position, yeah, that's time series data. If you're trying to predict, oh, what's the next position going to be, time series. One way you can do it. Now, if your number of inputs, though, really small, maybe you don't need to downsample it with all these weight-tied neural networks. If it's small enough, you can still do fully connected, okay? All right? Just be aware of that. Because it is time series, maybe you don't need to do it. Other questions? All right. So, with that, here. We're basically, we have 15 minutes left. All right. So that's all I wanted to cover for CNNs today, because I'm not prepared to code it up with you all today. I think that would be a fun thing to do Thursday. Yeah, sounds good. Okay, so just for the last 15 minutes, because just a little addendum, okay? Okay. From Thursday's lecture, okay, was the 26th. Okay, because we went through a couple things. We went through a little bit of clustering, and we never got to go through like the classifier, like a linear classifier. Okay, so I'm going to give a little primer on just how you would do a linear classifier, just because I didn't get to the end of class there. Okay, the idea, so we have a linear classifier. So there are no neural networks to be seen here, just a linear classifier. The idea is you have labeled data. So the labeled data. And let's just say that you have a bunch of red points over there and blue points over there. Or if you have a black pen, you can just imagine the colors. Okay? Where you have data x1 and x2. This is two-dimensional axes, right? Okay? And what you want to be able to determine is some way of saying, if you get a new data point, is it blue or is it red? Okay? That's different than clustering, where these didn't have a color. These were just black points, and you said, oh, look, that's a cluster, isn't that neat? Here they're labeled, so we want to be able, so we already know this is blue and red, and we want to predict, is it red or is it blue? Okay? The way we can do that, creating a linear classifier, draws a line right down the middle, right? If it's above that line, it's blue. Below that line, it's red. So simple, it feels like a Dr. Seuss book. Above the line is blue. Below the line is red. The dog is under the house eating a car. I've been reading to my son. He doesn't eat the car. Okay. The Go Dog Go. Anyone know Go Dog Go? All irrelevant. Okay. Professor talked about Go Dog Go most of lecture. Okay. All right. Okay. So the idea is that you could say, oh, you could classify, or you could say that if x2 is greater than or equal to some w1 times x1 plus b, and it is blue. You always say otherwise red, or you can also say that, if x2 is less than w1, sorry, it's x1 plus b, say, is red. Okay. We can do that with our eyes. That's not a problem. And certainly we could do this in higher dimensions than these 2 dimensions, at which point it becomes 3 dimensions instead of a line. 3 dimensions, it's a plane. 4 dimensions, it's a hyperplane. Okay? So, but the thing that you want to do, but the thing is, there are many ways you could draw this line that classifies them correctly, right? But some are going to be better at generalizing than others, okay? If I drew my line like this, okay, and it's really close to some of these blue and red dots, just barely, right? Then if I got a data point that's just over that line that is red, it'll trip over to the blue. Okay? So how do you create a very mathematical algorithm to not do that, so it generalizes well? Okay? What you do is you try to maximize the distance between the closest data point on either side. And the distance between a point to a line is just a linear equation. Okay? So it's actually a very simple optimization problem to do like this, okay? All right? So what you want to do is to maximize generality, you want to make a classifier that predicts the largest distance to the closest point on either side. Sure, that was a survivor trying to give me a spoiler. Either side. All right. What's that? Oh. Guy in charge of $500,000 for my lab. Get back to him. All right. All right. So, okay. So, all right. And on closest on either side. Let's see. Closest point on either side. That's what you want to do. That's good for generality, right? Okay? Now, we don't have time to go over the exact formulation to update that today, but you can imagine that distance there, right? Being as big as possible. That's for a linear classifier. But obviously, this is not going to work for an example that looks like this. Here are your reds. Here are your blues. Are you okay? You seem concerned. It is crazy indeed, right? You can't do a linear classifier there, right? Nothing you can do to separate those. Well, that's where your neural networks come in, friends. Because because a neural network can take something that looks like a line and then morph it into something squiggly, to use a technical term, right? So you can morph it into something that looks like that. That's when you need nonlinear classifiers. Neural networks are great for that. We'll stop it there. Time to digest that. Thursday, we'll be back to remote teaching. Okay? So hopefully it goes well. Have a good one.